now let's see the question number 2 of assignment number 1. So in question number 2 there are 3 parts. In the first part you need to explain whether the given circuit will be in continuous conduction mode or discontinuous conduction mode and the reason for that. In the second part, the voltage VST is given as plus minus 300 volt 50 hertz square wave, and you need to plot VT output voltage, input current, the IT, source current IST, and IDT, that is the current through the diode under steady state. And in the last part you need to find the ripple factor and V naught average. Okay. So let's see. So for the first part, let's see how the current waveform should be for this particular circuit. Okay. So now there will be some voltage now. If the diode we should name it like D1 and D2, this is L, this is R. So if the diode D1 is forward biased, how the current will be? The current through the inductor or current, this I current IT will increase because then the inductor will be connected to the supply. Okay. So suppose diode D1 is forward biased, and as a result of that diode D2 will be reverse biased. Okay. So the circuit will be like this. Okay. So this current I, from the moment that diode D1 is forward biased, the current I will start increasing, and current I will be like this. The shape of the current I will be somewhat like this. Okay. Then suppose what will happen, that the diode D1 is reverse biased. Diode D1 gets reverse biased. So what will happen? There will be some current in the inductor. So the inductor will start dissipating that current through the resistor and the diode D2. Okay. So the current will start decreasing. So the current will start decreasing exponentially. Okay. Till the diode D1 become forward bias in the next cycle. Till then the current will be decreasing. So the equation of that current that is decreasing, exponentially decay, the equation will be, this decaying current will be somewhat like this. the equation will be like some constant a multiplied by e to the power minus t divided by tau. Okay, so if this current does not reach 0 before the next cycle, our converter will be in continuous conduction mode, and if it reaches 0, then our converter will be in discontinuous conduction mode. So if someone asks what will be the when it will reach 0, so that is it, when it will be equal to 0, a e to the power minus t by tau is equal to 0. That means e to the power minus t by tau equal to 0. And what will be the value of t? If we see, if we take the log of this whole equation, this will be minus t by tau. And what is the value of log 0? Log 0 is minus infinity. So that means this current will reach 0 at t equal to infinite. So that means that actually this current never reaches 0. Okay, so our converter will be always in continuous conduction mode. Okay, the current might get very low, the value of the current might get very low, but it will never be 0. That's the property of any exponential decay. Okay, so this was the part 1 with the explanation. Okay, and the part 2, now let's go to the part B of the problem. In part B, we are given that the input is the VST is a square wave of 50 Hertz and the magnitudes are 300 and minus 300. Okay, so if you see here, this is the VST. So if you apply like that VST, what will be the voltage appearing across the diode D2? The voltage will be like this. We are plotting V voltage across the D2. Okay, this voltage. So where D1 is forward biased, the whole voltage 300 volt will appear here, and when the D1 is reverse bias, the D2 will get forward bias and this voltage will become 0. So this is how the voltage will be. Okay, so this is the voltage, we know this. Now let's see the question. We need to first of all plot V naught T, IT, IST and IDT under steady state. So how can we plot it? V naught T, IT, IST and IDT. Okay, so the V naught T is again the voltage, output voltage across the resistor. Okay, so this will be different than VDT. Okay, VD2T we have already plot. Now let's analyze it a bit further. So basically what happening is that this is your L and R, and this is the and here you are applying this is the voltage, source voltage for this LR combination, and this voltage is like this, a square, not a square, like it's a pulse of 300 volt magnitude, like this. Okay, so from the analysis of network theory we know that the LR circuit, how LR circuit behave. Suppose this is the voltage, 300 volt is the voltage, a DC voltage applied here. So what will be the response of the LR circuit? We already know, you should know this, that in the steady state the inductor will be short circuited, so all the voltage will appear across the resistor R, and the current, the value of the current will be 300 divided by R. Okay, so steady state value of the current will be 300 by R. So the current will be, the waveform of the current will be like this. Okay, it will increase from 0 and reaching to 300 by R. So this is the current waveform. And similarly, the voltage across the resistor will be, voltage across the resistor will follow the same but just multiplied by R. So this will be the voltage across resistor. Okay. So this is the response of the circuit. This is how the circuit will behave. So for this duration, you know how the response of the circuit is. And similarly, when this voltage is 0, that means there is a short circuit. 0 means short. So the L and R are connected. L and R will be connected like this. When your VD2 is equal to 0, so L and R, and there will be some current, initial current, so the current will decay like this. Okay, so the overall response will be is the voltage, so the current will start from 0, it will reach a value, particular value, and that value will depend on the time constant of the circuit and the frequency of this applied voltage. Okay, so after reaching this value the current will decay, then after that the current will start decaying. Okay, and then again it will increase, exponential increase, and then again it will decrease. Okay, so this is how the I naught t, the plot of I naught t will be. Okay, so this is the general shape. And similarly, if you want to plot, let's say V naught t, that is the voltage across resistor, so you just need to apply multiplied by R, so that will be like this. Okay, so this will be V naught t, this will be I naught t, but this is not enough. We also want to have some values in any plot. Okay, we need to give some mathematical values of particular at that point what is the value of this waveform, that also we need to include, then only our analysis will be complete. Okay, so what we can do, we can start our analysis from t is equal to 0. We will calculate this current. Okay, what will be the value of this current? We will first of all calculate the waveform, and then with the help of that waveform we will calculate this value of this current. Suppose we give it some value, let's see, this is the value of x, current value x, and then based on this value will be final value for this duration, and it will be initial value for the next half cycle. Okay, and so we have the initial value, and then also we can calculate the value of y and the value of z also. So similarly we can do, if we find these values, then we can plot these values, and then our plot will be complete. Basically the waveform will be complete. Okay, so how to calculate these values? So let's see some calculation during omega t equal to 0 to omega t equal to pi, because the frequency is 50 Hz. So this we are talking about this duration. So this duration, if we plot the circuit, will be like this: 300, and at t equal to 0 the switch is closing. Okay, this LR, and here it is V naught T, and IT is flowing like this, I naught T. So the equation of I naught T will be, you should be able to write it now directly, 300 R divided by R minus e to the power minus T by tau. Okay, so this is the value, this is the equation, or this function represents the current IT. Okay, now if you want the value of current X, what is the X? X is the value of current at a particular time. Okay, so X is the value of current at omega t equal to pi. So you need to calculate the value of t at, so that you replace t in this equation and you get the value of your current. Okay, and the tau is also given. The tau is L by R. So L is basically 0.3 and R is 100. So this is 3 millisecond. The time constant is 3 millisecond. And X, what is the X? X equal to I naught T at t equal to pi by omega. So for 50 Hz, what is the value of omega? For 50 Hz, omega is 100 pi. Okay, so if you replace omega equal to 100 pi, it will be 1 by 100, and so t is equal to 10 millisecond. T will be coming out to be 10 milliseconds. So you just need to put t equal to 10 millisecond in the equation, and also put the value of R. So it will be like 3 multiplied by 1 minus e to the power minus 10 by 3. So the value of x will be 2.89 ampere. Okay, and similarly now how we will calculate the value of y? We have calculated this x, we have calculated. This is our x. Now we want to calculate y. How to calculate y? So for y, we will have to write the equation of it. Omega t equal to pi to 2 pi. Okay, so what is the circuit diagram for this? Will be, this is connected to the source LR, and I0 minus equal to 2.89. This you need to remember. The initial condition is not 0 anymore. Okay, so at omega t equal to pi there was some current in the inductor, so you will have to use this for solving your equation. And with this condition, if you solve the your equation, the value of the current or the expression of the current will be I of t dash will be equal to 2.89 e to the power minus t by tau. Okay, okay, so this is the I value of it dash. Now why I am writing t dash? It is because we don't want to complicate our calculation, that's why we are assuming some t dash. Okay, so what is this t dash? T dash is the value of time. T dash axis, for t dash axis, this is the 0 value here. Okay, so you can write basically t dash equal to t minus 10 millisecond. Okay, t dash equal to t minus 10 millisecond. So at 10 millisecond, at t is equal to 10 millisecond, t dash equal to 0. Okay, like that you will have to calculate. So in order to calculate y, how we will calculate y? So for y is the value of this current at if you see y is the value of current at t is equal to 20 millisecond. Okay, for 50 hertz frequency the total duration will be 20 milliseconds. So y is basically at t is equal to 20 millisecond or omega t equal to 2 pi. So that is the value of y, the value of current at t is equal to 20 millisecond. So in that equation, t dash equation, what we will have to put? T dash equal to 10 millisecond. Okay, because t is equal to 20 millisecond. So y equal to it dash for t dash equal to 10 millisecond. So you just put the value 2.89 e to the power minus t dash equal to 10 millisecond divided by tau is equal to 3 millisecond, that we have already calculated tau, value of tau. So the y will be 0.10 ampere, something like that. Okay, so now we also have the value of y. Okay, so that is enough in order to plot the waveform. We don't need to calculate any further, but we will calculate some more things here. Okay, what is the thing that we need to calculate here? We want to calculate the IDCT, the value of DC current, or how the average is changing with respect to time. Okay, so the DC, basically the DC component of current we want to plot. Now how we can plot the DC component of the current? We drew the circuit diagram, we can draw it again. We know that this combination of L and R are subjected to a voltage like this. Okay, it's a periodic waveform, 50 Hertz frequency. Okay, and 300, this is 0 volt. Okay, so like this waveform is there, L and R we know. Now this waveform, if we convert it into Fourier series, this will be composed of some DC value plus some AC values. Okay, so if you only want the response due to the DC value of the input, then you will get the DC value of the output. Okay, so let's see what will be the DC value of this waveform. Okay, if you want to calculate the I naught DC of this waveform, so this is the waveform, this is 300, this is 0, this is pi, 2 pi, like this. So the DC value is the area under the curve divided by total duration. So you need to calculate this area divided by 2 pi. Okay, so this area is 300 multiplied by pi divided by 2 pi. So VD2 DC the DC value of this waveform will be 300 into pi divided by 2 pi. That will be equal to 150 volt. Okay, so if you want to analyze only the DC part, then what you can do is that you can connect a battery of 150 volt DC, and like this you will get the DC part of the current, IDCT. Okay, we are basically applying the superposition principle here. Okay, so what if I convert this waveform into its Fourier series? There will be a DC component and there will be AC component. So I am telling that the total response will be summation of the responses due to DC components and the AC component. So I am calculating the response due to only the DC component of the waveform of the voltage. Okay, so obviously the response due to DC component of the voltage will be a DC current. So this IDCT will be 150 divided by R 1 minus e to the power minus t by tau. So r is 100, so this is like 3 by 2 1 minus e to the power minus t by 3 millisecond. Okay, because tau is 3 millisecond. So this is how the DC component of the current is behaving. Okay, so this is the DC component, and we can also plot this DC component also. So let's draw the complete waveform here like this. Okay, this is thin red. So now let's see the DC component. Let's first plot the DC component. Okay, so the time constant is 3 millisecond. Okay, so if you have studied control system, then you will know that if the time constant is 3 millisecond, the current will reach its steady state in approximately 4 time constant. Okay, so till 12 millisecond the current, so the DC current IT will reach its steady state till approximately 12 millisecond only. Okay, so if you see this is 10 millisecond here, this is 20 millisecond, this is 30 millisecond. Okay, because the supply frequency is 50 hertz. Okay, so in 4 time constant the DC current will reach its steady state. So by 12 millisecond it will already be reaching, so 12 millisecond will be somewhat like this. So by this time you should be careful that the DC current will be like this. Okay, so this is the IDCT, and what is the total current? We have also know that the complete waveform of the current will be like this. We have calculated this value. This was our X, the value was X, this was Y, and this was, so the current will continue. So let's continue the DC current. So you see in the red color we are plotting the IT, I node T. Okay, so this is the I node T, that is the complete waveform, and in the black color we are plotting IDCT, that is the DC component of this waveform. Okay, Now one more thing we noticed, that approximately at the half cycle only the DC component was reaching its steady state. Okay, so if the DC component has reached the steady state, that will mean that this point X and Y, they will also be reaching their steady state. Okay, so this points X and Y will be more or less remain the same throughout this waveform. We don't need to calculate anymore. Okay, suppose we don't need to calculate Z here. Why? Because Z will be approximately equal to X, because the DC component has already reached this steady state. Alright, so in that way we also know the ripple component, the peak to peak ripple in current. Okay, in order to calculate that, we just need to subtract I peak to peak will be X minus Y. Okay, but in general we cannot do this, but in this case we could have done this, because the DC component of the current was already reaching steady state in half cycle only. If that steady state was taking longer, then you cannot apply the same process, because what will happen, that there might be a situation, suppose a particular waveform, so it's like this. Okay, now it is reaching the steady state and your voltage was, this was the voltage, applied voltage. Okay, so this is the DC component, and now if you plot the I naught t, the I naught t will be like this. You see, this value of X and Y will be changing according to the DC component, because DC is nothing but the average values. Okay, so you can see this here, this is X, this is Y, this is Z. Now here X and Z will not be equal, because the current DC component of the current has not reached its steady state till now. But in our case, in this particular problem, the DC component of the current is already reaching steady state very quickly. Okay, so we don't need to have to calculate any further. So this is I naught t, and in order to plot V naught t, you just simply have to multiply I naught t by resistance R. And also you need to notice this, that this plot here, suppose let's name it figure 2.1. so this figure 2.1 is not according to scale. Okay, because this is 300 and this is 3/2, so obviously this is not up to scale. That also you need to keep in mind. So if you want to plot the V naught t in the same diagram, then you will have to take the value of I naught t to be lower than what has been represented in this particular diagram. Okay, so I think the plotting part is over. We have plotted V naught t, IT, IST and IDT. So this is very simple now. You know the I naught t. So IST will be the current waveform in the positive half cycle, because in the positive half cycle the diode D1 will be conducting, and so So under steady state, so we should not start from 0. If you want to plot under steady state, then we will start from 0.01, sorry 0.10, because we have calculated this value that the current will be starting from 0.10, it will be going till 2.89, and then the IST will be 0 here. Then again in the next cycle, this will begin from here and reach till here. So this will be like IST will be, for negative half cycle it will be 0, and from positive half cycle it will go from 0.10 to 2.89. Now if you want to plot the IDT, so IDT will be the remaining part of the current. So if you plot in that same diagram, you can plot now. So in the red color we are plotting IDT. So in the red color this is IDT. IST, this is IDT. Okay, so the part 2 is complete. Now part C, find the ripple factor in V0 average. So the part C of question number 2, ripple factor. So ripple factor is basically RMS of the AC component only divided by the DC value. Okay, so for that you will have to calculate the RMS of the AC component only. So in the total waveform, you will first of all you will have to calculate the RMS value of the complete waveform, and from that value if you subtract the RMS of the DC part, then you will be having the RMS of the AC part only. Okay, so this is one way to calculate the ripple factor. There is another thing which is peak ripple factor. Peak ripple factor is actually much easier to calculate, in which you need to this is like V peak to peak value of the voltage, output voltage, divided by the DC value of the output voltage. This is also very famous parameter. So if you want to calculate the V peak to peak, then we will just do is we will multiply R with 2.89 minus 0.10 divided by V0 DC. Okay, so in the steady state, what will be the value of the DC component? That will be equal to 150. Okay, that we already have seen. So V0 DC is basically 150, and R, the value of R is 100 ohm. So if you put it in this equation, you will get it. So peak to peak ripple you can calculate like this, and if you want to calculate the ripple factor based on the RMS value, then it is somewhat difficult. Okay, so generally you can also use peak ripple factor. Okay, so the remaining part is the V naught average. So V naught average we have already calculated is like 150 volt, because the again the same argument is there that the V naught average here, you see this, so V naught DC we already calculated, if you have seen here. So here only we are plotting it now. This is the VD2, this is the voltage applied across this L and R, and the average value of L in will be equal to 0. So this average value will be equal to the voltage across the resistor only. Okay, so the VDC, yeah, V naught average equal to 150. So based on that only we have done the calculation. So this is how you can solve the question number 2. Okay, now let's see quickly